Like previous work, we use neural networks to predict the motion of a fluid over time, but with the central goal to increase accuracy and robustness of long-term predictions. We propose to use a joint end-to-end training of both components, the fluid state compression and the temporal prediction of the motion. Such a joint training allows both components to build a holistic view of the underlying task. Another key observation is the need to control the learned latent space. We therefore propose structuring the latent space through subdivisions. It enables us to precisely adjust parts of the latent space to adhere to physical behavior determined externally by well-understood classical methods. The subdivision is enforced with a split latent space self-constraint for the input quantities velocity and density, and hence allows for alteration of the individual encoded components separately. This separation is a key component to robustly predict long-term sequences as demonstrated by our results. The autoencoder enforces spatial compression and yields our latent space domain C. The second part is the prediction loss. This includes our temporal prediction network that advances the state of the simulation in time by iteratively predicting the next time step based on the last predictions. The last part is our latent space split. This loss enforces the separation of input quantities, velocity and density in the latent space domain C. The split schematic shows the result of our split loss, where we enforce a clear separation. This means we know which part of the latent space corresponds to which input quantity. With this knowledge, it is possible to exert precise control over the prediction in the latent space domain. The no-split variant will be shown on the left, our proposed method in the center, and the ground truth on the right. Since our initial goal was to propose a method to enable long-term predictions, we also evaluated predictions ranging over a longer time horizon than before. The example demonstrates the temporal instability introduced by networks without temporal constraints, due to the accumulation of error. In the previous examples, we have seen that our method stays close to the ground truth, whereas the no-split version is less detailed and at times deviates strongly. In the following, we demonstrate how the different methods react to a second inflow region that was not seen during training time. To go even further, we added a solid obstacle to the moving smoke prediction. The moving smoke networks haven't seen an obstacle during training. In the following, we will show some predictions of our 3D moving smoke scene. We observed that our method scales better with increasing simulation complexity than a classical pressure solver. This led to a speedup of around ×9 in complex 3D scenes. We propose a neural network-based long-term prediction method with the advantage of being able to easily modify the latent space externally to meet the desired needs, such as boundary conditions.